All right, so good morning all. Okay, so last um, Monday, so we stopped at the Newton's third law, right, where we learned that when still remember that the experiment. So when we have the motion, the cut in the motion to the right, and then we have the wind, okay, the wind from the fan, the left, okay, and then that is moving. All right, so but after we block the wind, all right, after we block the wind from the card, so the card stop moving, so it just stays static over there because of the Newton's third law. All right, for example over here, so we look that we have when we kick the ball, so we have, let's say, force as A, so we have the force A on B, which is force from object A exerts the force on object B. All right, and then we have another force of FB, which is the object B exerts force on object. Right, so when we have the force in both directions, so the force will cancel. So that's why we have the card. So in that case, so we have the card is not moving, right? Okay, let's say we have an object pulls back on you just as hard as you pull on it. Okay, so how can it ever accelerate? Okay, so let's say you look over there. So we have, let's say we are having a huge block. Okay, so where we have the friction force on floor, on the block, on the left side, okay, and then we have the force, okay, there is an action and reaction pair, okay, so where we have a people, all right, so a mason trying to pull the block, okay, so we have both force acting, right? So we have Fm, so the force from mason on the R, okay, on the rope. So we have the rope there, okay, and then force from the rope on mason. All right, so Fr on M. Okay, so the mason remains at rest if Fr on M is balanced by the friction force on the mason. So it is only moving, okay? It is only moving when Fm is bigger than, okay, than Fr on M. Right? So the block begins sliding if, okay, Fm on R overcomes the friction force on the block. Okay, so whenever the force Fm on R exceeds the friction force, then the block will move. Okay, let's say we look at example over here.
Here I have a magnet. If I place it on this base and read the scale, it reads 56 grams. Now this base allows the magnet to float a few centimeters above it. When I place the magnet on the scale so it will float, what will the scale read? Will it read 0 grams, 56 grams, or negative 56 grams?
Okay, what's your answer? So let's say the magnet is put on the scale, all right, above the base, and then the scale has been zeroed to subtract the weight of the base. Okay, so what do you think of the weight of the magnet? All right, is it A, 56 gram, B, 0, and C, minus 56 gram? Okay, so what's your answer to that? Who says it's 56? Okay, let's go back to the and then we see.
Here I have a magnet, and if I place it on this base and read the scale, it reads 56 grams. Now this base allows the magnet to float a few centimeters above it. When I place the magnet on the scale so it will float, what will the scale read? Will it read 0 grams?
Okay, so what will it read? Is it A, B, or C? So A is 56, all right, B is 0, and C is minus 56 gram. So who says it is 56 gram? You can raise your hand. Okay. Okay, so we got two students, so Munra and Lim. Okay, so how about 0? Okay, how about minus 56? Okay, I mean says minus 56, so let's see.
56 grams or negative 56 grams.
So the magnet is placed on the base and the scale reads 56 grams. Now the scale doesn't read 0, it reads 56 grams because of Newton's third law. The base is pushing up on the magnet to keep it floating, but in the same time, the magnet is pushing back down on the base with the same amount of force.
Okay, so what's the answer?
Here I have a magnet, and if I place it on this
56.
base and read
Right,
the
so the
scale,
answer is
it reads
56.
56 grams. Now this base allows the magnet to float a few centimeters above it. When I place the magnet on the scale so it will float, what will the scale read? Will it read 0 grams, 56 grams, or negative 56 grams?
So the magnet is placed on the base and the scale reads 56 grams. Now the scale doesn't read 0, it reads 56 grams because of Newton's third law. The base is pushing up on the magnet to keep it floating, but in the same time, the magnet is pushing back down on the base with the same amount of force.
Okay, so the reading on the scale is 56 gram, okay, which is because when you put the magnet on the scale, all right, so it will have a force acting on the magnet, and then also the magnet have the force acting on the scale or the base. All right, so the force is pushing down and also the force of pushing up. All right, so but initially when you already put the base on the magnet, all right, it's already okay, so the reading is already set to a 0. Okay, so the reading is already set to 0. So that's why you have 56 gram on the reading of the scale. All right. it's a little bit tricky when it comes to the Newton's third law. So I hope it will be clear when you do the exercise later on the Newton's third law. Okay, let's say we have a simple act, all right, of walking depends crucially on Newton's third law, all right. So let's say we start moving forward and you push backwards on the ground with your foot, right? As a reaction, the ground pushes forward on your foot, okay? And then hence on your body as a whole with a force of the same magnitude, okay? So this external force provided by the ground is what accelerates your body forward. So it's like when we move, okay? So when we walk, okay? So okay, when we walk, so of course we will push ourselves. So like it's like we push ourselves forward, okay? But actually, okay, we push it backward. So the force is actually going backward. All right. So as a reaction, so the ground pushes forward on your foot. Okay. So the ground pushes forward. So from the ground pushes forward on our foot. So that's why our body is actually having the force moving back, and the foot, our foot is having the force pushing forward. Okay, so why we can move forward? Because the force, okay, the force that is applied from our foot is much better or much bigger than the force, right, that push our body backward. Okay, so sorry, the force that that push our body forward. So the force of the body, okay, so the force of the body, so it's like this. So when we move, so force on the foot going that way, and then this is the force from the body. So this force is higher, and then this force is lesser. So that's why we can accelerate. All right. So that's actually about the principle of movement of our body. Okay. So let's say we have a sprinter over here. So the force of the starting block on the runner has a component that counteracts her weight. Okay. And a large horizontal component that accelerates her. So that's why you look at the sprinter, okay? So you look at the sprinter. Why the sprinter stand to actually trying to make it vertical, okay? Try to make it vertical. Try to make it horizontal. People try to make it horizontal with the ground because okay, because she wants to get the highest momentum as possible. Okay, so that she can accelerate faster. So it is actually the science in the sport or the physics in the sports. Okay, so that's the strategy. How about if you actually sprint? Okay, that's why you can try by yourself. Try to sprint starting from using on the straight body, right? But on the second experiment, you try it by making yourself a little bit horizontal with the ground and see what's the result. Okay, you can try that. So this is what I mean. Okay, so you just stay straight, okay, and then you run, okay, until the finish line. So this, let's say this is the finish line, okay, and then you have another one of yourself, okay, so like that. All right, so see what's the result of that. Okay, you can see what's the result of that. So you timing of, so you take from there to there. You can try to stop your watch. Okay, let's say, of course, I believe if according to the physics law, so by doing like this, you will get uh, you will be much faster compared to the first experiment. Okay, so the first one. All right, so you see over here, so we have the force. Okay, so the force on the block, so it's going that way. So we have the component of fx and fy. You can see that the component of fx is much larger compared to fy. Okay, which fy is cancelled. Okay, fy is cancelled due to the weight. All right, so you have a bigger force on the fx. All right, so let's see. We have another one. Okay, so this guy, so using the basketball game, so we have, okay, one player, okay, is uh, jumping, okay, and then you see the other guy, okay, the other guy wants to defend, all right, he wants to defend, okay, by blocking the player on the white shirt, all right. So what he needs to do, he must jump, right? So he must jump. So to get it as much as high as possible, so that player must first push down, try to push down his feet on the ground, okay, and then will increase the upward reaction on the force end, okay, on the floor on him, okay. So because that other player is already jumped, so when he jumped, so he's now in the free fall motion, okay, where he has the weight, okay, where he has the weight only based on the gravitational force. All right. So, but the other guy is going to start to jump, so he can push his feet. So, in order to make a force of n upward, all right, to counter the force, the weight force, all right, which is the gravitational force. All right, so that's it for the Newton's law of motion. Okay, so any questions so far before we're going to continue on the next topic? Now we are going to look at the how we can apply the Newton's law. All right, so we are now in the chapter 5. So here we will learn about on how to use the Newton's first law to solve problem. Okay, Newton's second law to solve problem. Okay, nature of different types of friction forces. Okay, the how to solve problems involving the forces. Okay, the key properties of the four fundamental forces of nature. All right, so the Newton's three law of motion. So we have first one, second, and third one. Okay, can be very simple, but applying this law to real life situations requires skills and problem solving techniques. Okay, in this chapter, we will begin with equilibrium problems, in which we analyze the forces that act on the object that is at rest or moving with constant velocity. Okay, we will then consider objects that are not in equilibrium. Okay, first we will consider the object in the equilibrium first, right? And then later, we will consider object that are not in the equilibrium. All right. So when the object is in the equilibrium, okay, so when it is at rest or moving with constant velocity, okay, in an initial frame of reference. Okay, so as a principle of the Newton's first law, we have the summation of force will be zero. Okay, because the object is at rest or at a constant velocity. Okay, and this will be equivalent of summation of the force in the fx direction will also be zero, and also the summation of fy will also be zero. Okay, so how to solve this? So we need first to draw a sketch of physical situation, and then we draw the free body diagram, and then if the mass given, then we can use the equation of W equals to mg, so relate that with the weight. And then check only that if you have included the force that act on the object, so is the normal force and also the friction force. Okay, all right, and then we choose a set of coordinate axes and include them in the free body diagram. Okay, so all right, so let's see the way. Okay, one example on how to do the problem for Newton's first.
Example 5.6, an ice boat is at rest on a frictionless horizontal surface as shown in this diagram. There's a wind blowing to the right that produces a force we're going to call F sub W on the boat. The other two forces are, of course, the weight of the boat, which acts straight down, G, and there's a normal force from contact with the ice acting up. We're told that the boat starts at rest, and then 4 seconds later it's moving at 6 meters per second. And from this information, we'd like to calculate the wind force on the boat. So let's begin with a free body diagram. Here's our positive y-axis, here's the positive x-axis, and all the forces in the problem lie on an axis. Normal force up, the weight down, and the wind force to the right. We make note of the parameters given in the problem that the velocity starts at 0, then after 4 seconds it reaches 6 meters per second. So let's write down Newton's second law for the system. sum the forces in the x direction, which is only the force of the wind, and that must be equal to the mass times the acceleration in the x direction. In the y direction, however, there's no motion, and so the sum of the forces must be 0. There's no acceleration either in that direction, so n minus mg is equal to 0, so I find that the normal force is actually equal to mg. For me to calculate the force of the wind, I really need to know the acceleration. I have the mass, which is 200 kilograms. But I can use this kinematic equation to calculate the acceleration, since I know the initial velocity and the final velocity. When I solve for acceleration, I get 1.5 meters per second squared. Plugging that back into this equation, I find that the force of the wind is 300 newtons, or about 67 pounds. Notice that this force is actually quite a bit less than the weight, or the normal force. The weight, in this case, which is mg, is 1960 newtons. The reason, of course, it's so much less is that the acceleration is actually very small. If this acceleration were 9.8 meters per second, then the force of the wind would actually be equal to the weight of the boat. And this ends example 5.6.
Okay, so
Example 5.6.
so we have a problem.
Rest on a frictionless horizontal surface.
Okay, so we have a problem of a boat. All right, so the boat is moving forward. Okay, so if we have the ice boat is at rest on a frictionless motion horizontal surface. So there is no friction. So when there is no friction, of course, the boat will be moving. Okay, a wind is blowing along the direction of the runners, so that 4 seconds after the ice boat, it is moving at 6 meters per second, about 22 kilometers per hour, 15 miles per hour. Okay, what constant horizontal force Fw does the wind exerts on the ice boat? So basically that's our Fw. X was what was drawn. Okay, combine the mass of ice boat and rider is 200 kilogram. Okay, so Fw is to the right. Okay, because we have the force of the wind. Okay, so that move the forward. Okay, and then we also have normal force and also the weight force. So the weight is equals to mg. Okay, so we have the x and y component over there. All right, and then the initial velocity, okay, v naught x is equals to 0. Okay, and then at times t 4 second, so we have vx equals to 6 meter per second. All right, so as we assume that, so the total force, okay, the total force on the y-axis will be 0 because we have plus n minus mg, so we have n equals to mg. And for the fx, because the boat is moving, so we have the acceleration. So the acceleration times mass, so we obtain our Fw. Okay, so how to obtain the acceleration? So we use the equation of motion. So we have the Vx equals to V naught x plus Axt. So our V naught x will be 0, and then Vx is 22 is 6 meter per second, right? So we put 6 meter, so that will be equivalent to Axt. Okay, so 6 divided with 4, so what we obtain, it is 1.5 meter per second squared. So that is our acceleration. So the acceleration times mass, so we have 300 kilogram meter per second square. Okay, so that is our FW. Okay, this guy actually checked. Okay, so 300 kilogram meter per second squared is equivalent to 300 Newton. Okay, so this force actually much less than the force, okay, the force acting on the ground, which is the weight. Okay, where the weight is equals to W equals to mg. Okay, so G is 9.8. Alright, so which is much bigger than the moving speed of the boat. Okay, so that's why he obtained that the equals to 1960 Newton. Okay. All right. Okay, let's look at, so that one was about the Newton's first law, and then we look at the Newton's second law. So we have the dynamics problem. So we apply Newton's second law to object which the net force is not zero. Okay, so these objects are not in equilibrium and hence are accelerating. Okay, so we have the Newton's second law where F equals to ma. So just before that, the example combines the F, okay, of the Newton's second law and also the first law, because the object is moving to the right, okay, but it is moving on the x component, but it's not moving on the y component. All right, so equivalently, so we have summation of fx equals to max and summation of y equals to may. Okay, so ma, okay, the acceleration does not belong in the free body diagram. Okay, so only the force of gravity acts on this falling fluid. So remember that. So when there is a free fall motion, there is the speed is actually does not depends on the mass. Okay, it does not depends on the mass. It just depends on the force of gravity acting on the falling nut, for example, falling fruit, for example, over here. Okay, so how about the free body diagram? So how about the free body diagram of the free fall motion? Okay, so we can safely draw the acceleration vector to one side of the diagram. So this is correct. So we have W down going downwards and also AY downward. All right. So we have the incorrect. Okay, so we also have the incorrect way to draw the free body diagram. So it is not equivalent to the MA. So because as I said, it's not that it does not depends on the mass. It just having the acceleration where the acceleration is the gravitational force. Okay. All right. So this is the way. So step by step that you must check on how to solve the problem. So you can read it by yourself. Okay. So let's go to the where we have, okay, what we call that as an apparent weight and weightlessness. Okay, when a passenger with mass m rides in an elevator with y acceleration AY. A scale shows the passenger's apparent weight to be N. Okay, so we have the normal force. So you remember, because the elevator or the lift, okay, going up and down. So we have normal force and also W. Okay, so where the W over there is equals to mg. Okay. Okay, but the weight is showing that the W equals to, okay, m in the bracket g plus a y. Okay, so the extreme case occurs when the elevator has a downward acceleration. Okay, ay. Okay, when ay is equals to minus g. Okay, that is when it is in the free fall motion. Okay, when they're in the free fall motion, we don't even feel ourselves. Okay, we don't even feel ourselves. I don't know whether you have this experience or not. So might be you can, if you want to try that, so try to jump a little bit on the something uh, on the way, but make sure that the ground is soft, okay, to avoid the injury to your body. Okay, let's say you try to jump. Okay, let me give example, a diving situation, all right? On diving, when you dive, when a diver try to dive from a height, let's say from 10 meter and to the swimming pool, all right? So during that motion on the air, it is on the free fall. So actually the diver won't feel the mass of his body. Okay, so that's why it is occurs at the extreme case where ay is equals to minus g. Okay, so in that case n is 0 and the passenger seems to be weightless. Okay, so this is what the concept of apparent weight it is. All right, so similarly, so we have an astronaut, okay, orbiting the Earth with a spacecraft experiences apparent weightlessness. Okay, uh, the doesn't feel, okay, doesn't feel his body. Okay, just feel like he's floating somewhere. Okay, uh, on the space. All right. So this is because there is no gravitational force acting on his body when he is in the space. Okay, so for the friction force, so there is a friction between the feet. For example, we look at this caterpillar. Okay, the larval stage of ship butterfly of the family Papilionidae. All right, so this is the caterpillar and the surfaces of which it walks. So let's say it walks on a big apple. All right, so without friction, the caterpillar could not move forward. Okay, and climb over obstacles. So it will just slide. Okay, we just slide on the apple. You know that the surface on the apple is smooth, right? So it's smooth. So it is, if there is no friction, okay, no friction between the caterpillar and the apple, of course, the caterpillar will slide. So we won't be able to climb the apple. Okay. All right. So when an object rests or slides on a surface, the friction force is parallel to the surface. Okay. So the friction force is parallel to the surface. Okay. So the friction force, let's say on the y component, right? So we on the X component. So we have the normal force on the Y component. So we have, okay, so we can, let's say we have a contact force. So that contact force is a force so that can be expanded into the friction force and also the normal force. And we also have the weight acting on that normal force, so it cancels out, right? So we have the push or pull force, right, to the x-axis. Okay, so the friction between the two surfaces arises from the interaction between molecules on the surface. So because we have the molecules, so that's why we have the friction. Okay, so as you can see that we have the block and the floor. So if we look, we magnify it. So we look at the friction and normal force results from the interaction between the molecules in the block and in the floor where two rough surfaces touch. Okay, so when there is two rough surfaces, so you can see that when it is a rough surface, so at the, if you magnify it, you can see that the surface is not smooth. So there is some curvy spaces on the block and also some curvy spaces on the floor, right? So that's why there is a friction. So that's why there is a friction. Okay, so the kinetic friction acts when an object slides over a surface. Okay, the kinetic friction force is Fk, okay, equals to mu k n. Alright, the static friction acts when there is no relative motion between objects. The static friction force can vary between 0 and its maximum value. Okay, where the maximum value is, okay, Fs should be less, okay, equivalent to mu s n. Okay, so we look how we to understand this kinematic friction. Okay, so before the board slides, okay, the static friction acts, okay, but once it starts to slide, the kinetic friction acts. So that's the two different friction, okay. So we have the first static friction, okay, and then another one is kinetic friction, okay. So the static friction when the board is at rest, okay, so there is a static, so we call it static friction. And when we move, there is another kinetic friction, okay. So kinetic is when the object is moved, static when the object is at rest. Okay, so over here, there's no applied force, so there's no friction. So Fs equals to 0. Okay, so here we have, okay, let's say we apply a weak force. So let's try, we are trying to pull this, all right. So when we pull this, okay, actually I applied some force to move this calculator, all right. As you can see that it won't move. Okay, you try to push, but actually there is a friction between my hand and this calculator, so it won't move unless you apply a bigger force, so it can move. Okay, when you apply a very small force, it won't move. But if you apply a bigger force, of course it can move because the force is already overcome the force of the friction. Okay, over here, so this is an example where I apply only a soft force. Okay, so when I apply soft force, the object is still at rest. Okay, so so here what we call as the static friction. Okay, so Fs now, so before this Fs is 0, there is nothing. Okay, there is nothing, so I don't put my hand over here, so there is nothing, so that's when Fs is 0. But when I put my hand here and try to pull it, so like this, so we have Fs as a value, but it's less than mu s n. Okay. Alright, so next, when I apply a bigger force, so now Fs is equals to mu s n. Alright. So before the board slides, the static friction acts, but once it starts to slide, the kinetic friction acts. So you can see those three situations. First, when there is no friction, because the object is at rest. Second, when I try to pull it, so that's when the static friction acts. And then lastly, the third one, when I pull with a bigger force, so we have the kinetic friction. Okay, and then when the board sliding at a constant speed, okay, like this, it's constant speed. Okay, so the kinetic friction, so we have Fk. Okay, so we have Fk equals to mu kn, right? Mu kn. So we have another moment. Okay, look back over here. Okay, so we have like this moment before this. Okay, when I put a weak force, okay, it's not moving at all. So over there, Fs is still static friction, less than mu naught s. So this is the maximum of static friction where it is about to move. Where it is about to move, then we have the static friction at the maximum. Alright, at the maximum where mu s n. But when this calculator starts moving, alright, when it starts moving, then we have Fk. Okay, Fk is the kinetic friction. Okay, so before we stop, let's look at this video.
Example 5.13, you want to move a 500 Newton crate across a level floor. To do this, you can apply a 230 Newton horizontal force to get the crate moving, as shown in the diagram. And after it breaks loose, you'll be able to keep it moving at a constant velocity with only 200 newtons. Given this information, we like to calculate the coefficients of static and kinetic friction. Let's begin by looking at the forces acting on the crate. There's the weight down, which is 500 newtons. There's a normal force up. Here's the tension that's being applied to cause the crate to move. And of course, frictional force opposes that motion and it pulls to the left. I will take the positive x-axis in this direction and the positive y-axis straight up. Given these forces, we can write out the free body diagrams for each case. The case just before the crate moves, I have a normal force up, the weight down, the tension to the right, and now my frictional force will be at its maximum value. It's the maximum value of the static friction since nothing is moving. After the crate begins to move, however, the static friction converts to kinetic friction, which is a somewhat smaller force, but again it's still pointing to the left to oppose the motion. And my tension is less. Now also, it's only 200 newtons. So let's apply Newton's second law to the case just before the crate moves. Here are the forces in the x direction. Here's the maximum static friction force to the left. And they have to sum to zero since nothing's moving and the system is still in static equilibrium. And from this, I find that the maximum static friction force is 230 newtons, which is, of course, the applied force. In the y direction, the normal force is actually just going to be equal to the weight, which is 500 newtons. Now I use the definition of the maximum static friction force as simply the coefficient of static friction times the normal force, and divide this value by the normal force as shown here, and I find the coefficient is 0.46. Notice this has no units. After the crate starts to move, the equations for Newton's second law look very similar, but this is now going to be a kinetic friction force. The normal force is again 500 newtons. Using the definition of kinetic friction force, I can simply divide by the normal force, and I get the coefficient of kinetic friction is equal to 0.4. If I look at the solution, I note that the coefficient of static friction is larger than the coefficient of kinetic friction, and this is usually the case. And this ends example 5.13.
Okay, so I hope that's clear for you. So we have the mu k, right, and mu s, which is the coefficient of the static and kinetic friction. Okay, so you can go back and then look at that. I'm going to share you the slides, all right, to the WhatsApp group. Okay, and then so we stop here for today. So we're going to revise that again on Monday, all right. So please turn on your camera so we can take the attendance together today. All right. Please turn on your camera. Okay, come on everyone. So, all right, I'm going to count from 10. All right, so 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and smile everyone. Okay, give me one more shot. Okay, and one more. All right, so I see you on Monday. So, all right, so shortly I will share you the slides that I just that we just learned today. All right, so have a good day and have a good weekend. All right, so I see you next week. Okay, assalamualaikum and bye bye. Okay.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.